We always do a brief, for those of you who've joined us before, we do a brief embodied carbon 101. Essentially, in the life of the built environment, it goes through all these stages: extract raw materials, transport to factory, manufacture the products, transport to site, construct to the building or infrastructure. Operational emissions is what we think about when you're using and maintaining the building. It's turning on the lights and running your air conditioning. And then on the back end, demolition, hauling away the waste, and landfill. And of course, when we're thinking about a circular economy, that last piece actually disappears and becomes the raw materials for the cycle to begin again. But that is a separate conversation that we will not be talking about here. This is the pie chart showing where global CO2 emissions fall, and that 28% of building operations was something that the sustainability community was really focused on, I'd say, for the last 15, 20 years. And we've really gotten a handle on that one. Net zero buildings are pretty common. People are pretty comfortable with them. The additional where you see concrete, steel, and aluminum, and then that dashed line going into industry, that's all the emissions connected with producing the materials that become our buildings. And that, I would say, there's been a steep increase in interest and understanding of what that is. And we see concrete there as 11.1%. That's 11.1% of global emissions. It's huge, one material. Now, addition to that, we talk about the time value of carbon, which just sounds so interesting, I know. And we've got this bar chart, and everybody loves bar charts. The yellow is the embodied carbon. Again, these are emissions, CO2 emissions that happen in the production of materials and getting them to a building site. The blue bars are operational energy. And another way people talk about embodied carbon is upfront carbon. So it's all the CO2 that's been emitted at by the time the building infrastructure is finished. So that's just, it's already emitted from day one. The operational carbon gets every year, you use more operational carbon. So that's stacking up year by year. Year one, it's X, year two, it's 2X, year three, 3X, and there you are. Now, when we're talking about this now 9-year window to shift our emissions profile, you see at 2030, embodied carbon is actually a larger piece than the operational carbons. And that's why we're doing what we're doing. We're trying to highlight, we're focused on what we can do to change the emissions of our materials. Particularly today, concrete. So this is an article that came out in The Guardian last year, 2019. And so concrete is the single largest emitter of CO2. Steel is a close second. They're next. And it's worth digging in a little bit where that comes from. So concrete, as you may know, is it's water, cement, gravel, or aggregate, it's frequently called, and sand. The sand and the gravel is inert. The chemical reaction comes from the water and the cement, which hardens to become concrete that we know. The emissions come from creating the cement. So it's really, of those 4 ingredients, it's really the cement that's creating that really high CO2 emissions. You can see in the upper, on the left side, limestone calcination. So to make cement, you take limestone, you burn it at a very high temperature. And in that burning, CO2, like 50% of that total emissions comes from what comes out of the smokestack of the chemical reaction of turning the limestone into cement. Another 40% is the energy used to get those high heats, and then you've got an additional 10% in transporting the concrete to where it needs to go. So without further ado, when we created this event, our goal was really that you all could go to your kitchen table or wherever your workplace is currently, and tomorrow morning, and make some changes in how you deal with concrete to reduce its environmental impact. And we invited these 4 rock stars in the space, and they all accepted, which is why we're really excited, and we're so thrilled that you have all come to join us. So I will just briefly introduce them in the order that they will be presenting. First up is Dirk Kestner. He's a structural engineer and the Director of Sustainable Design at Walter P. Moore, which is an international company with structural and civil engineering, building enclosure, diagnostic services, traffic, transportation, and parking consulting. Followed by Don Davies, who's also a structural engineer. He's president of Magnuson Clemenczak Associates, structural and civil engineering firm based in Seattle with global reach. Don is also a founding member of the Carbon Leadership Forum, our parent organization. Both of them will be talking about case studies that projects that they've done in the LA area. John Halverson is next. He's the Director of Technical Services at National Ready Mix Concrete, ready mix supplier serving the California market. And he'll talk about what National is doing with EPDs to facilitate mix optimization. And then finally, we have Alana Guzzetta of US Concrete's National Research Lab, who will be sharing latest innovations. That'll take us to about 6. We'll have until 6:30 for Q&A. So with that, Dirk, take it away.
Right. Thank you very much, Jill. All right, let me share my screen.
As Dirk's getting set up, just thanks for setting the stage there, Jill. If anyone has any questions, please feel free to drop them in the chat, and we'll collect them as the presentations go and order them at the end. Thanks.
Awesome, Luke. We're looking good. So
look good, Dirk.
Awesome. I will start with a case study on the City of Hope administration office building and kind of the pieces as we'll step through. And Don and I talked about our presentations before, and we kind of aligned them in chronological order. But this one really was before there were a lot of EPDs in Southern California. So it's a kind of an early story and one of what you can do even if you don't have EPDs. The leading ready-mix suppliers do, and we need to be advocating for that, and I know we'll be talking about that more, but there's things you can do prior to them as well. So I've got the, I'll go through it quickly because Jill did a nice job, I'll call it the 099 version of concrete and embodied carbon, but then talk about the project through the implementation and tally, the motivations, a little bit about LEED and the baseline we used, and then I'll close with that important relationship between embodied and operational carbon, and we actually kind of plotted this for our project. So the project is the City of Hope administration building. Here's the rendering. It's the building over on the right by the dam. The owners, City of Hope, it was designed by Gensler. We served as structural engineer, enclosure engineer, and performed the whole building LCA. It's about 100,000 square feet, a little less. But it's a building that had sustainability goals throughout the design. Early on, everything from mass timber to other strategies were considered. But you know, operationally, it's very efficient. It's under 40 kBTU per square foot per year. It's electrified. It's got almost 40% on-site PV. It's in the process of seeking gold. So carbon was considered throughout the design. And then time-wise, you know, we were going through the concrete submittal process in early summer 2018. So this is what we were working through with National and the team and the builders back then. Here's the rendering. Here's the project as it's built. It's always kind of nice when enough or a lot of what was in the initial renderings made it through, but a lot of exterior circulation and a really just great looking building. When you strip that back, it is a concrete building. It has a lot of concrete within the building. Probably as we looked at it, about half the concrete, give or take, is in the PT floor slabs. maybe 30%, give or take, is in the foundations, with the balance being in the core walls and the columns. And each mix, each use really has a different mix, has different things you can do with it. And that's a real important thing to consider, because while all the concrete may look the same to the untrained eye, the demands far beyond strength, but placement, exposure, aesthetics, they're all different. So each mix needs to be considered individually. So if we strip this back, the concrete, and look at it, say, as a slice through a cylinder, we see it represented by volume. And we see that an awful lot of it is from the gravel or the aggregate, with the paste and the sand kind of filling in the spaces in between. And we can look at that same cylinder by weight and look at it by mass, and we see that most of the weight is in the coarse aggregate and the sand, with the balance being cement. The white, I'm representing some SCM in the water. But, as Jill said, one thing contributes disproportionately to the CO2, and that's the cement. And things can be done with different types of cement, but the cement is the piece that is really dominating the CO2 of the concrete. A key that I want you to take away from all of this, and because a lot of people specify this way or think of it and say, are we using fly ash? It is not about fly ash. Reducing the embodied carbon of concrete is about reducing the embodied carbon of concrete. It's not about putting fly ash or slag or an SCM into the mix. If you do need a proxy, you might use the cement content. But we've been kind of keeping our mixes internally, charting this and looking at this, because a lot of people ask us these questions. And here's a chart of 400 mixes plotted of GWP on the vertical axis versus percent SCM across the bottom. And you see that there's a whole lot of scatter. Some of the, over those mixes on the left that are, quote, 0% SCM are, less impactful than 40% SCM. But if we plot that against cement content, we get a much better line, one that has a pretty good correlation. So as you start to think about this, and as you start to think about it, ideally we want the EPD number, but the cement content can be a proxy, much more accurate than the GWP number. So just getting back to the building, I mentioned that sustainability was an important part of the design throughout. And one of those pieces was both to kind of have a lot of the circulation outside that we can see in this picture, also to expose the concrete and minimize those finishes. So as the project was considering its LEED approach, what LEED level it would seek, and where it was going to get the points as it went through that, one of the credits that was identified was the whole building LCA credit, or the life cycle impact reduction credit, which for the new building is the whole building LCA. So in short, if you're not familiar with that, that means that you conduct a life cycle assessment in scope to structure and enclosure, and then based on where the impacts are and what you find it's the hot spots, you explore your design, make reductions, and if you achieve 10% reductions, you can, without something else going up by 5%, you're awarded the points. This was done under the LEED version 4 framework. If we got into the LEED discussion, it's become more granular in V4.1, but we could talk about that in Q&A if people wanted. The process is really simple. You use a model or your bill of materials, which we represented by the Revit model on the left, not of this building, of one that's got a few more floors. But then you use a tool. In this case, we use the Revit plugin Tally that has all the data for the materials, and then you perform a comparative analysis. So at the building scale, this is what the City of Hope Administration building looks like from the Tally run. And we see a lot of yellow. The yellow is the concrete. That's kind of what I would call your eye to, and that's what we found when we did our first run. I don't know if my mouse shows up on here. I'll take the chance that it does. This deepest yellow at the bottom is the cement. So we see kind of across all of these comparative analyses, we see a lot of deep yellow, showing that really the key to making these reductions, both in global warming or embodied carbon, but also some of these other impacts, is really how we're using cement and if we can minimize cement. But that's trickier than it sounds, because we need to think about who really determines what's in the concrete. And I've shown this as kind of the org chart, if you will, of our team on the project. And at the lower left, you have us as the structural engineer who prepare the concrete specification, but that gets handed on the design side up to our client, put together in the project documents, that goes through the owner and then comes over to the construction team that we had in this case, which was Hathaway Dinwiddle with Chlorman and then National Ready Mixed. And it goes through each one of those parties. And the thing that we found that's the single thing that people can do to achieve reductions is figure out a way to break down that that silo or those two different groups, and think about this as a collaborative team. And we found that it really can be very productive when there's a two-way discussion, and the engineer and the specifier needs to really respect and listen to the ready mix designer and not just have some hard requirements that they're forced into. But as the whole team talks and understands why each requirement that they're putting on their spec is causing something, or is driving, say, the cement content or the embodied carbon of the mix. So one of the pieces that we found for our floor concrete, which was about half the mix, was to use the Polaris aggregate that comes from British Columbia. And this just kind of shows the map, and then it's barged down the West Coast. And a lot of people think, how could it, we've been trained in previous versions of LEED or sustainability rating systems for local materials, part of that being to minimize transport impacts. But how can this possibly work? And we'll kind of talk about that later. The other piece let's see. All right, oops, going the wrong way. Apologies for that. All right, the other piece as we're looking at these comparative reductions is to make sure that we are measuring from an appropriate baseline. For our project, we used both the National Ready Mix Concrete Association report. At that time, it was the version 2 report. Last fall, the version 3 report came out, and the appropriate regional mixes, because as this map of the US shows, and it's quite more granular than this, but NRMCA has grouped it at least by some states, that because of local practice, local aggregate availability, the proportions really can vary significantly. And this is for another mix in LA, but it shows the concept of how how shipping the aggregate a great distance can actually achieve embodied carbon reductions. So if we look at a baseline mix where the embodied carbon is dominated by the cement, the higher quality aggregate can actually cause a much greater reduction in cement content that still is a net win, even when you multiply, say, the transport impacts by a factor of 3 or 4 or more, and you burden it there. So if we come back to our LCA plot from Tally, and Tally doesn't quite let you, you have to do some workarounds to get the transport burden put back in, so we had to freehand it in as the orange. But what we see is that by using our optimized mixes, which for the floors consisted of using Polaris material instead of the local rock, and for the foundations and some of the elements consisted of lower cement, longer times till strength, mixes that used high levels of SCMs, we still come out as wins under all of the impact categories. So finally, just kind of closing this with the bigger picture and putting the embodied and operational emissions together for this project. One of the things, especially if you're in California, to understand, and for projects that are electrified, the California grid is much cleaner than the national grid. This is kind of a pull out from the EPA power profiler that you can use to find any sub-region of the country. But if we look at the California grid compared to the national average for CO2 per megawatt hour, it's a little bit more than half, but it's also getting cleaner. So if we were to plot the embodied and operational emissions based on the EUI, based on the power sources for the project, this is what it looks like kind of for reference, that we have this upfront investment burp, is some people call it, but this hit that we take, and then the operational emissions build up over time. I've kind of shown here for the project what it would look like if it didn't have the on-site PV, and then with the on-site PV it gets cut down and the slope becomes flatter. And then if we look at this in combination, we have our reduced embodied carbon that we show as the actual deeper shaded red. Then we go up the slope of our low operational impacts. But also if we think about the goals for the California grid, and if it is to become, all renewables by 2045, this line actually just goes horizontal and, really just flattens out there. So with that, I will close and transition over to Don.
Unmute myself there. Thanks, Dirk. And this will stop others from sharing, yes. So are you guys hopefully just looking at my screen? It says MKA at the front right now?
Yes.
Okay. And let me get to the one that I need to. So I think what I'm going to talk about actually is quite complementary to everything that Dirk has just shown you, and going to build on it a little bit more with another example. Because I really do want to focus again on this interface of what happens between design and construction to reduce the embodied carbon of our new buildings. And so I'm going to talk about process first and foremost, and some of the context around how we can quantify and then act on embodied carbon, building a little bit on what Dirk was showing there, but start to talk about environmental product declarations and how those are changing what we are doing. And then I'm also going to show a few case studies of this, what this looks like in practice and where we can go. So to start, I want to give a shout out to the Embodied Carbon and Construction Calculator, or EC3, because it really does target this crossroads between design and construction. It's only part of the carbon reduction story for sure. It doesn't do all of what an LCA gives you, but it's an important one. Now, EC3 at its core is really, it's just a database of these environmental product declarations from across the nation, but making them accessible for timely decision making. And the effort to create EC3, it started at Carbon Leadership Forum, and it was a collective action effort that included more than 50 different partners in the AEC industry. So it's creating an ecosystem to make this whole conversation a little bit easier. And what we've really found is by collecting these EPDs in one location, it really does help enable and inform purchasing decisions. And it really starts moving the industry, because when people see themselves being what we're measuring, what we choose to focus on, people can't help but compete on it. And so it's one of the real value propositions that comes with it. So at the heart of tracking EPDs or any of this embodied carbon modeling, the math is actually really pretty simple if we can do it. It starts with the design community, especially us as the structural engineers. When we're talking structure, we've got to know our quantities. We need to track our quantities, we need to estimate them throughout the project, and we need to use that in decision-making steps to know, are we being efficient in what we're doing? Once we know our quantities, though, then you want to multiply those quantities times an environmental product declaration, or the information that would come from those. Industry average numbers like the NRMCA ones that Dirk was just showing exist out there in design before you know who your supplier is going to be. And certainly as the suppliers start coming on board, getting those mixed specific EPDs or the rebar specific EPDs and using that information to then refine the quality of your data is important. The math is actually pretty simple when you add those two things together. The trick is really in our ability to consistently and accurately track our quantities and to consistently and accurately get that carbon data to be able to do something with it. Remember though, whenever we start making this too complex, pull it back to keep it simple, because it really should be a simple process. Quick LCA, whole building LCA study. This is for a project up in Seattle, but I use it also a little bit like the tally information that Dirk was showing to give us order of magnitude where we're paying attention. That lower graphic is the tally results for this project of all of the shell and core of the building. The real message in that is the A1 to A3 section, the materials, the concrete, the steel, the wood, that go into creating the building. That is, on the embodied side, is the driver of embodied carbon, and that's why it's such a high priority to spend our time there first. And then if we look closer into that A1 to A3 category for this project, the concrete is without question the biggest driver was of the carbon footprint of that building. Then it's steel. This building happens to be a mix of concrete, steel, and wood. The wood, actually, I'm showing here is a variable because it really depended on the carbon footprint of where the wood was sourced and what end-of-life assumptions you make with it. But any of those, in comparison to, say, the thermal and moisture or the openings and glazing or some of the finishes, it's still being driven by and large by the structure. So as that last image showed, if we pay attention to concrete and we focus on here, one of the things that is most actionable for concrete is, I'm going to talk about, is performance-based mix procurement. And Dirk mentioned that a little bit. It's real important to start working with your suppliers early on. But the more we can get away from prescriptive mix designs and only specifying what we really care about, and then letting the designers do what they do, let them come up with the mix criteria. That is, in fact, how we can usually drive to get the lowest carbon footprint solutions. The correlations that Dirk was showing was exactly right. It's not about how much fly ash you put in the mix or slag or other SCMs. It's much better to say, hey, what do we really need? Such as we need 5,000 PSI concrete in our shear walls. It has a certain exposure classification. I might have a shrinkage or a modulus criteria I want to know. Only give it that criteria when you really need it, so we're not putting overburden testing requirements on our ready mix suppliers, but then frankly get out of the way and compete them on dollars and carbon footprint. Don't tell them how to make the mix, let them make the mix to meet your criteria, and then just look at the EPDs afterwards. The more we can do that, the more we are actually going to let the experts do their jobs and for what it is they actually do. So we know our quantities, we performance space the mix designs. What's the next step? We need to get it into our specs to make this ask for the information, especially on EPDs, because it starts with the specification. And I'll always remember this comment the first time we were talking about trying to get EPDs and carbon information from our contractors on a project. And the guy looked at me and he just said, you know what, hey, this really isn't my topic, but my job is just to follow the specification. Give me the spec, tell me what you want, I'll make it happen. And it was kind of a watershed moment. It's like, specs matter in a really, really big way with our supply chain. And so we got to get the specs right. Keep it as a simple ask. But the project I'm going to talk about here in a moment, actually, we also did not have EPDs at the start of the project. But by, frankly, putting this in the specification requirements for the project, asking for this data at the time of bid, actually, when bids happened, we didn't get EPDs. We used the proxy of the amount of cement that was in the mixes. But by having it in the spec before the project was done, we actually did get the EPDs all the way through, and it's become, I think, a major differentiator for National, who ended up doing this project and being able to show their leadership of what they're being able to do with low carbon concrete. So you got to get it in the spec. You also need to change your bid documents and work with your general contractor to make sure that that ask in the specification makes its way into the bid, so that we're asking these hard questions. And we're focusing on concrete right now, but it affects steel and other materials as well. Keep the ask simple, but keep it very targeted and make the ask. When that happens, that project I was just showing you about, this is data from a project in Seattle, not necessarily in LA, but a very similar story is coming out. Performance-based mix criteria, minimal criteria, but just what we needed. Ask the suppliers, though, to give EPDs for each of those mixes and compete them against each other. And in the case of this project, the winning supplier was 31% below the NRMCA regional averages for their area. But more importantly, for our client, also that winning supplier not only had the lowest carbon footprint, they were 18% lower carbon footprint than the other supplier. They were also the lowest cost. because we got out of their way and let them do what it is they need to do. So this creating these win-win scenarios, these are the stories our clients are going to run with all day long. And these exist in the industry today simply because we haven't been asking for the data. We don't ask for the carbon data. And I look forward actually when it gets harder to do these kind of variables, but it is what's in the market today. So back on EC3 for just a moment, this is a sample of the EPDs that are inside of the EC3 database right now. And just for how quickly this is moving through our industry, when we started talking about EC3 and its creation, there was, I think, a total of 800 EPDs that existed in North America that we could grab hold of. Today, there's over 28,000. In the concrete ready-mix market alone, we have over 26,000 or 27,000 EPDs inside of EC3. So this topic is moving very quickly, and clients are responding to it, and markets are responding to it. Here's just a quick map for you of where EPDs exist that are inside of the EC3 database. So without question, it's West Coast and in our West Coast cities that are dominant where this information exists, but it's moving across the country. And I think it's only going to be a matter of time as this map starts to get quite a bit darker. Some of the things you can start doing inside of EC3 once we look at this, a little bit of some of that comparative data that Dirk was looking at. Here's a look at just the sorting of all the EPDs inside of EC3 for 5,000 PSI concrete in the Pacific Southwest, so basically California, Nevada, and New Mexico. Now I'm just showing 5 different suppliers right here, but you quickly can start dialing in for a particular mix. What are the ranges we might be able to expect to see on the carbon footprint or of those mixes? Where's the NRMCA regional benchmark? For the Pacific Southwest, you know, that NRMCA average is actually pretty close through the middle of the data as you would expect. Inside of EC3, we also set a high benchmark of what we call the CLF baseline, which is where we try to ensure at least 80% of all mixes are going to fall below that line, as you would expect. So that's on the high side. So this is actually really good about where you would expect to see the data. Now, there's some regionality in here that isn't totally a fair comparison. There's the Central and the CEMEX numbers are both from mixed designs in the Bay Area, where the national information is in LA, and partly through the aggregate information and what has to be imported or what you're doing with local. The mixes are different, so there's always a regional effect. Just looking at a national number isn't enough. But what's nice about EC3 is this data is all being aggregated in one place where it's free, and we can start looking at it and start helping inform what it is we're doing. So bringing this to this example in Los Angeles, this is the Brookfield's 945 West 8th Tower that's currently under construction. And we also looked hard at, in our initial spec on the project, we asked for what we needed. We got mixed designs coming into us through the general contractor. Before the bid was made, though, we did the comparative evaluation to talk about carbon footprint of those mixes and looking at what the suppliers were able to do, looking at the EPDs. And in that sync, the first mixes that came to us, actually none of them used the imported aggregates of the Polaris rock coming from British Columbia, which using the local rock supply, because of its inconsistency, one of the reasons the cement content is so high in a lot of mixes in LA is that higher cement content is how they manage that inconsistency in the rock. So when you bring in the higher quality rock, the very consistent aggregate size, aggregate quality, you're able to tighten up that bell curve. And it's why we're able so much to take so much cement out of these mixes while still getting exactly the same design strength on a project. So what did that mean on the project? On the total project, the single intervention of using the imported aggregates was a 24% carbon footprint reduction across the entire project from what we had as baseline mixes, not against NRMCA, but mixes proposed for this project using local aggregate versus going to the imported aggregates. In fact, it was up to a 47% reduction in cement on the post-tension mix we were looking to use. So asking these targeted questions, it's meaningful, it's substantive, and this is something we all can be doing today, embedding the ask for EPDs into our mixes. You know, depending on where you are in the region, some suppliers are going to have these and some aren't. But what I love seeing is once a major supplier does start to produce these EPDs and National is clearly leading the way and driving on this, the others have to, if they want to stay in the competition, they have to come on board. And so I think it's only a matter of time that this really does start to show up across the region. I want to talk about another thing on the project though too, beyond just what we can do in the mix designs on the aggregates. You know, one of the other challenges that we had on this project is we have a big thick mat at the base of the tower. It's a big tall tower. And how we were going to deal with hot weather concreting to be able to pour that concrete in the August timeframe when this happened created actually another win-win scenario. And I'm using this to highlight other places that we can get both carbon and cost reductions if we're willing to work with our suppliers. So on this, the first proposal was for the project to match what happened at the Wilshire Grand Tower, which frankly is right next door across the street, where they installed chiller pipes down in the foundation to cool the mat foundation to keep the temperature down. But those chiller pipes and that cooling system in the mat brought with it about a $1.5 million price tag and a significant uptick in terms of coolants and refrigerants and steel and piping that was going to have to go into the mat, strictly to deal with the means and methods of how you're able to build that mat without it tearing itself apart because of the high heat that would happen by pouring in the summer months. But what we did is we challenged that option. We worked very closely with National and with the general contractor Webcor, and went back and looked at every part of the material supply chain. What could we do to reduce the thermal component of that mix before it got to the site? Part of that included changing the mix, taking cement out of the mix, more SCMs going into the mix. It also went into, we did a whole testing program of just how high we thought the temperature could go on the mixes we were going to use before we started to have problems. But what really was one of the biggest interventions was looking at that aggregate supply and storing those Polaris aggregates, not at the batch plant, but storing them down by the water where we had better natural cooling and a natural lower temperature, and then simply protecting the rock, putting the cover over it. That lowered the temperature of the rock by 15 to 20 degrees before it actually even got to the site, or got to the batch plant, and did a just-in-time delivery to put it in the mix and bring it to the site. A series of intervention strategies with those, coupled with some ice. The long story short, we were able to cut 2/3 of the cost out and greatly reduce the carbon footprint of what was going to be our mat foundation requirements to go in for this tower. All of this really is what is possible when you're working with your contractor, when your suppliers, with a cross combination, and not trying to just be in our silos with the criteria. So one final thought on that I want to throw out there. Now, this is not the 945 West 8th project, but this is actually showing our Aqua Tower in Chicago. But very often, what's going to control the concrete in our projects, it's not the final strength that we are specifying as structural engineers. There's a lot of other things that come into the project to drive its performance. And so think for a moment, just compare what happened on this project where they used column hung flying table forms, which allowed the slabs to stay fully supported for 3 full days, 72 hours before the shoring was ever stripped. And the reshore load never came onto the slabs because it all went directly onto the columns. Compare that to what would typically happen today. In fact, how we're building West 8th, which is a typical 3-day per floor cycle. It means stripping horizontal formwork at 24 hours, stressing a PT deck probably at about 48 hours, and then reshore loading kind of in that 48 to 72 hour range that is going to load the slabs up when they're still green concrete with the heaviest loads that they're probably ever going to see in their entire life. My point with this is simply that forming system choices greatly drives the performance requirements that have to go into our mixes. And you know, we're not using table forms that much these days for a number of reasons, but don't just take things at face value. Be inquisitive. Look at what's options. Look at what we can do as designers. Look at what the contractor's real needs are to meet their performance objectives. And you may find some very unique directions where you end up going to be able to solve those problems. And so for that, hopefully this gave a few ideas to help inspire some action there. With this, I'm going to, for interest of time, I'm going to move it off to our next speaker, which I think is going to be John. Is that right?
Yep. Thanks, Don.
Okay.
John, can you hear us? Get share screen.
Okay, you got me?
I got you. Yeah, perfect. Yeah.
Thank you. Let me see if I can get my screen shared.
We see it.
There we go.
Great.
All right.
Take the floor. Thanks, John.
Well, I want to thank you all for having me participate here. It's a privilege to be associated with such leaders in the industry. My name's John. I'm the Director of Technical Services at, can you see my screen okay? Is everything good? Okay. Director of Technical Services at National Ready Mix down here in Los Angeles, California. Really our sustainable heavy lifter is Shibata Godkar. She's our concrete environmental engineer, so I have to give her props. You know, a couple of weeks ago, we had a brief conversation on the phone about concrete in Los Angeles and why Los Angeles was slow to respond to sustainability, understanding the local capabilities of the local market, and how to lower the environmental impact of concrete now. Did my, you can give me the thumbs up, Dirk. Did my screen change? Sorry.
We're still seeing the title screen, John. There we go. Yep.
This, like this. Okay. Well, so these were kind of the agenda items that I had on my to-do list. I realized that Jill had mentioned that I was going to really focus on what we are doing to optimize mixes, but I didn't really go into that direction, but I'll talk about it somewhat. Nice bluebird day in California. I'd like to see more of those. National's part of a global group called VCOT. They've been around for 165 years. It's a family-owned business. Anyway, locally in North America, they're a cement and materials company. There's a cement plant in Alabama, and there's one here locally in Lebec, which is just east of Gorman on top of the Grapevine, up in that neck of the woods. I don't want to spend a lot of time on this, but the Ready Mix Materials Group is here in the 3 counties in Los Angeles. Our sales and lab is in Ontario. So, you know, VCOT has a very broad commitment to sustainability, and that commitment led to an immediate approval of our commitment and our moving forward with sustainable concrete here in Southern California. But locally, what we're doing at the ready mix level is the utilization of supplementary cementitious materials, the on-demand EPD tools that we use, which Don had mentioned earlier, the use of the high-performance marine imported aggregates from British Columbia, water conservation in terms of recycled water, batching stormwater. We can't put any of the water out to the storm drain. We just invested in 50 new CNG ready-mix delivery trucks, and I believe 8 tractor trailers for interplant haul, and also investment in infrastructure in terms of CNG fueling stations. It's yet to be determined how those items are going to affect our EPD values, but most likely they'll be lower, but we haven't gotten to that point just yet. We're just starting there. So one of the items was, you know, why was Los Angeles slow to change in terms of sustainability? Part of its demographics, right? You know, more of the progressive projects and attitudes about sustainability have definitely been from the Pacific Northwest, including the Bay Area. As you move south, it's a little bit slower to change. Not that we're not willing to change, but the projects themselves are not really specified that way. You know, it's just been recently until projects that Dirk and Don were talking about that have even shown up down here. So in the traditional way of how things are done, you know, the ready-mix suppliers are basically, you know, doing what the spec says. So obviously the design and the engineering really drives that. The Bay Area is not as vertically integrated with cement companies as Southern California. I mean, you've got 5 major producers of Portland cement down here, right, which are vertically integrated with, you know, 4 of the major ready-mix suppliers, and another major one is vertically integrated with aggregates. So there's a lot of vertical integration down in the Los Angeles market, which is a little bit different than Northern California. And then some of the projects, right, that have been built up there are by big tech companies that have, you know, these sustainable goals that you know, they're trying to achieve. So it's just been a little slow to change, but you know, I don't feel like there's any reason that Southern California is minimizing the importance of it. It's just taken a little bit more time to get there down here. So things have changed. They're moving in the right direction. Here's LA, right? That's not a very pretty picture, but it's more of a conventional or traditional kind of market. Like I said, it's very much vertically integrated. There's a lot of small little companies, you know, that have little niche markets, and you know, they're not really required or have any desire to spend money and resources on, you know, getting into this new world. So I don't think we're really going to change that. But you know, for the big market downtown, it's definitely changing. You know, as far as supplemental cementitious materials to replace cement, this historically has been a fly ash market down here. Cemex has started to import slag from China into Long Beach, and that allows us to use higher amounts of SCMs. You know, fly ash does have its limitations in terms of performance past a certain percentage, and slag is more favorable there. However, as Don mentioned, slag may not be as favorable for thermal control where fly ash is. So they each have their benefits, but now we have more options down here. And you know, there's really been less of an awareness of sustainable low embodied concrete down here in Southern California. So just kind of logistics a little bit also plays a role. This is a picture on the left here, this black and white one of a plant that I started working at in 1987. It's up in Sacramento. It's a Teichert's Perkins plant. I believe it's still there. And then over here we have our kind of our new updated plant, which has a lot more capacity, a lot more silo capacity, a lot more versatility in what we can do. But generally, you know, a lot of the ready mix companies or the ready mix plants down here were built in the 1960s, right? So, you know, you look at this old plant, it might have, you know, 4 or 5 bins to handle different materials and maybe 2 silos to handle cementitious materials. You know, when they built these, they weren't thinking about sustainability, right? It was just get the concrete out. So you have this infrastructure in Los Angeles, right, that is slow to react to sustainability just because of logistics. But like I said, you know, and the problem is that you can't greenfield a new plant very easily. So, you know, something on the right there that has a huge capacity and lots of versatility is not the norm. But that plant it's a downtown plant. The trucking logistics are very challenging. And, you know, when you really look about it, you know, Ready Mix is a trucking company. And you can have a job in Santa Monica, let's say, or Century City that might be 14 miles away, and it takes you 80 minutes to get there. So companies aren't really that interested in bidding work that they're going to have to, you know, put half of their fleet on to service a project. So that's challenging. So, you know, when you're talking about your collaborative efforts, you know, you have to understand what production capability is around you and what versatility do they have to add all these different, you know, high performance aggregates and multiple SCMs and things like that to get your low goals, your low carbon goals. So you really need to understand what's around your project and who's interested in it. So that happens early on. We did talk about Don talked about the aggregates locally, which are good aggregates, right? They meet the ASTM requirements. And you can make sustainable concrete with it, you know, depending on what the performance requirements are. We've done low heat concrete with them and we've done high strength concrete with them, but they do have, they're kind of soft, I guess. And some, I mean, Corona has, down in Corona, they have a good hard aggregate. It's very strong. But when you compare that to, say, the imported aggregate from the Orca, it's very soft in terms of its concrete stiffness and modulus of elasticity. The water demands are not that great, so water demand is driving performance. So if you can lower your water, right, you can lower your total cementitious content. You know, it shrinks kind of normal, but if you have low shrinkage requirements, you might have to do something else or with the aggregate or throw a bunch of expensive admixtures in there. So, you know, you have markets that, you know, are back in this era where in the 60s where there's nothing better than good old 5-sack. So you have a huge market and you have to, the ready mix companies need to, you know, sell to everybody, I guess. So anyway, that's a little bit about that. Of cement. So this is a glamour shot of our cement plant in Lebec. But the cement companies are finally coming around to understanding that there's a global change to reduce the carbon footprint, and they're starting to change their views. Locally, us and other cement manufacturers are starting to produce PLC or 1L13, which is a limestone blended cement. So essentially, and I think Jill was talking about cement manufacturer. You know, when we burn limestone, it has embodied CO2 that's released during that operation. So we're not burning the limestone, we're introducing it after the kiln and grinding it into the cement. So essentially you have concrete that has 15, or cement that has 15% grounded or blended limestone in it. So by itself, limestone cement doesn't perform as well as straight cement. I mean, you've got 13% less sintered material in there. But sometimes people need water cement ratio for durability concerns or permeability issues. So strength may not be an issue, you just want the low permeability for maybe sulfate conditions or something like that. So, but what we've seen in our R&D is, and I'm sorry, mine's not, I don't have a lot of data here. Mine's more of a kind of a market summary, but we've run some R&D on these 1L13 cements with fly ashes and slag, and when you combine those materials with slag, is what we've seen at very high replacement rates of like 50%. We're actually exceeding cement control, straight cement, ordinary Portland cement control. So, you know, when you do that and you make these 1L13s with, you know, 13% less clinker in it, and then you're combining that with 50% of a SCM or a post-industrial product, you're really doing, you know, quite well and getting to some super low numbers in terms of the GWP or the embodied carbon of that mix. So they're doing that, but it goes back to the plant capacity, right? Okay, you've got your normal cement, now you've got 1L cement. You might have type 3 cement for high early something. You might have white cement for architectural. You might have slag, fly ash. You know, you're talking, okay, that's 5 silos. Again, we're back to the 1960s plants that don't have that capability. So it just takes time for you know, the capital to come through on the budgets to get these improvements on these plants. And some are doing it. I know many people are adding additional silos to their plants. As far as the fuel itself, you know, typically cement is manufactured by coal, right? You grind coal and you burn it in the kiln 24/7, and there's a lot of CO2 released there. So for many years, and even now, we're using alternative fuels such as waste tires and oils, even alternative fuels like petroleum coke and natural gas in some cases. At our plant, we use tires and pistachio shells, because there's a lot of fuel heat value in those, so we supplement coal with those. So there's other cement firms that are using wind energy for alternative electricity to run their plants. So I think there's more of a push now on cement manufacturers to lower their carbon footprint. Gosh, I wish I knew why my screen wasn't working, but so presently here in Los Angeles, right, as I had mentioned, slag has been introduced into the market, which is good. 5 years ago, Orcus, Polaris, Eagle Rock started importing, and we're finding many benefits to that. Many of the companies are producing values on their concrete through EPDs in one form or another. And there's an increasing awareness in the design community to design these projects collaboratively to lower the embodied carbon. So the EPDs, it's a big spot talk. Not every supplier has EPDs available to them. Like I said before, the small mom and pops, they most likely won't. It's not part of their base. I know that we, National, have partnered with Climate Earth to do product-specific EPDs on anything that we want to. There's companies that might do products type 3, third-party verified EPDs on a few of their mixes, which is okay. It limits their ability to be real creative sometimes, but they do have them. And then there's industry-wide. So generally, the industry-wide numbers have higher values and not as favorable as a product-specific EPD.
So just a quick time check here, John. So we have just in the interest of time for Q&A at the end. Just if we could wrap things up in a couple of minutes and give mindful for Alana's time too. Thanks.
Okay. Let's see. Just to mention on the EPDs, it's like as soon as those started showing up, some companies went full bore ahead and some didn't. But quite honestly, there hasn't been a lot of requirements for EPDs down here in Los Angeles. I could probably a handful of them. I'm not going to go into that or that. Like I said, we partnered with Climate Earth to use some tools. And with some of these tools, we can kind of do what Don was talking about, and we can make comparisons between, you know, a static design with local materials versus something with premium aggregates and higher SCMs. So these two columns, new and old, would show, you know, same performance type mixes with their associated GWP values. So in this case, although these are only comparing 1 cubic meter of carbon, showed a 27% reduction. If you added in your volumes on the job, you could be much more accurate. But this is where you can talk about in collaboration about trade-offs between, you know, this matte foundation with a 391 versus, you know, the PT slab, I don't know if that's right, has a very much higher number. And it's like, well, if we can load this one up with and extend the age of the performance requirement, then we could back off on some of those replacements here so the contractor can turn forms in 2 or 3 days. So that's some of the exercises that we can do now. There's the collaboration. It's very important. I don't want to just rehash what others have said. But what do you do at these meetings? It's like we talk about performance versus prescriptive specs. What are the durability requirements? What are your sustainability requirements? What's the contractor doing, right? You know, it's amazing. I'll have 3 contractors bid the same job and ask for 3 different things, right? 3 different ways of how they're going to do it. And then obviously the geography and all that stuff. So it's important to have this. And like Don said, if you have the suppliers in early on, I'm not going to talk about that, but this is bad, this is good. You know, do you really need to specify slump? No. Do you have minimum cement contents? No. This is what you're concerned about, right? The performance. So, anyway. Okay, so I'll pass it on, Dirk. I appreciate the heads up on that. If you have any questions about the ready mix down here in LA, you can get this contact information and contact myself or Shibata. And I really do appreciate the time that you gave me to kind of explain the market in Los Angeles. Thank you.
Great, thanks, John. All right, Alana, the floor is yours.
Okay, sounds good. Let's share my screen here. All right. Okay, well, so my name is Alana Guzzetta, and I manage the research lab for US Concrete. US Concrete is the parent company to a variety of ready-mix companies in different areas of the United States. And then Orca is also, the Orca aggregate is also part of our team as well. And while US Concrete is headquartered out of Texas, San Jose, California is the place for our research lab. So that's where myself and my team are based out of. In terms of kind of supporting being able to do performance specifications, this is just showing a guide that we created to try to help engineers implement that, or architects have that discussion with engineers. And what's shown on the screen is a lot, and it's really not intended for you to read right now. It's just shown what it is as a PDF guide, and this is something that we're happy to share with anyone. So it's something that I will provide to the Carbon Leadership Forum Los Angeles team, and anyone who reaches out to me by email, LinkedIn, if you're interested in it, feel free to ask. What it pretty much goes through is kind of three primary things that we tend to see that are prescriptive in nature, that being minimum cement content, maximum water cement ratio, and maximum SCM content, and just showing what we believe usually the intended performance is by specifying those, and then provided suggestions for alternate ways to still achieve that performance, but be more performance-based rather than prescriptive-based in nature. And then as well, this is just an example to kind of show where going a more performance-based route can take you. If anything, I really did this to kind of prove it to myself, because I don't like to talk about these things without feeling confident in it, or sort of seeing the example for myself. And so this is showing 4 different types of mixes, the red being a mix with 100% of the cementitious material being Portland cement, then the black being a 25% fly ash mix. The darker gray is a 50% ternary mix, so 50% of the cement is replaced with supplementary cementitious materials, and then the light gray being a 70% cement replacement. And so you'll see that as you replace more of the cement, the global warming potential, which is going to be that value found on an EPD, is being reduced. And then the other piece that this is showing is going from a mixed design that's designed to meet a 0.45 water cement ratio, and those would be the bars on the left. And then when you go look at the bars on the right hand side, where same mixed performance is trying to be achieved, and we're able to achieve it with these materials at a 0.50 water cement ratio, you can see that with these there's about a 7 to 12% reduction in the global warming potential. And so this just shows how going performance-based and not specifying water cement ratio unless it's required by an exposure class within the code, how this does allow further reduction in the embodied carbon of concrete. And then what this shows is just the breakdown of 3 different mix designs. And really kind of what I'm going to be showing here is something that Dirk also showed in his presentation, just sort of shown in a different way. And so with this is breaking down the EPD of 3 different types of mix designs. The light gray being a 50% cement replacement ternary mix. And what you see is there where you've got 50% of the cement replaced, the cement makes up about 74% of the total embodied carbon out of all the materials that are in that mix design. Then when you go to a 15% fly ash mix, the cement is going to account for more because you have less cement replacement there. And so now you've got about a 87% contribution from the cement, and then you're having a little bit of a contribution from the fly ash. And then when you go with 100% cement, that's where you're going to have a higher majority coming from the cement in that case. But then when you take this and you make the same plot for these same mixes, dividing it up by the volumes of each of these material in the mix, you can see that the aggregates are going to make up a significant portion of that. And so Dirk showed that visually with some great representations in his presentation. And so with that, your aggregates are going to make up about 60 to 70% of the volume of your mix. And so this just to show that while they are a smaller portion of the embodied carbon, they're not to be ignored because they're going to contribute significantly to the performance of the concrete, which then also drives where you're going to be on your embodied carbon for that mix. So then a few things I just wanted to go over is that there's a lot of mix design levers that a concrete ready mix producer has in terms of adjusting a mix design for performance and for lowering the embodied carbon. And so these are those that I'll be going through, and I'll go through each of them briefly, really looking at what is available today, and then also in most cases being able to talk to kind of what might be on the future or what might be the newer technology, and also trying to give some practical advice for each of these to kind of go off of what the goal that Jill laid out, and trying to have something that's very practical to follow. And all of this to say, to sort of continue the message of that communication with your ready mix producer is going to be very important because they're the ones who are going to, be able to speak to the availability of each of these types of levers in their market. So the ones we'll talk about are cement type, cement replacement materials, the aggregate selection, admixtures, sequestered carbon dioxide, and then the use of waste products and recycling. So when it comes to cement type, John did mention this. ASTM C595 type 1L cement tends to have a lower embodied carbon than an ASTM C150 type 2 and 5. The ASTM C150 type 2 and 5 is what has been most common here in the California market. And there are some markets in the country where this type of cement is already available, and it's very likely that this is going to be the standard coming up in the future in a variety of markets. And so an actionable consideration for here is to just include in the specification the allowance for an ASTM C595 or an ASTM C150 cement. And then that gives kind of starts the preparation for transitioning to having those available. Then in terms of cement replacement materials, this is talking about, another term for this would be supplementary cementitious materials, talking about things like slag and fly ash and things that have already been discussed. With this, the cement replacement amount is going to be dependent on what materials are available because they do, as John touched on, they do have different properties and are going to give different structural performance to the concrete. And the contractor's schedule is also very important here when you're proportioning a mix design. Something that I find interesting with supplementary cementitious materials is that they have really been used in concrete for a long time and have a strong history that really was started with the quality. They bring a great amount of quality to the concrete in terms of an improvement to durability. And it's only kind of in the recent decade where it seems like the attention is really going to then the environmental benefit that they do bring as well. But it's something that really started with the performance value that they provide. With SCMs, you can usually achieve denser concrete. You're going to get strength gain that builds up at a later age, which helps contribute to the durability and strengthening of the concrete. And you're also going to get corrosion resistance as well with these. It's also important to consider and communicate the architectural aesthetics that you may be going through for your project. So some actionable considerations are to allow all supplementary cementitious materials that meet an ASTM standard. And so products like slag, fly ash, natural pozzolan, silica fume, glass pozzolan, metakaolin, those all have ASTM standards associated with them to guide the quality on those. And so the more of those that you allow, the more flexibility you're giving to a ready mix producer to be able to incorporate those or for you to allow your project to go with whatever is available in the market. Then having a performance-based specification in this case is going to help. Something to consider as well is to specify your design compressive strength at ages later than 28 days when the schedule allows or the application is appropriate. And then again, making sure to communicate any architectural requirements with the concrete supplier is important. Things to consider for the future, there are new pozzolans being developed. So I mentioned glass pozzolan. That's something that an ASTM standard is newly coming out for. That's not something that's readily available in the country. There's a source in the New York market that I'm aware of, and that's the only one that I'm aware of right now that's available out there. Then additionally, as we continue to go into the future, the standard available sources are probably going to be changing. Fly ash comes from burning coal, and so as some of those sources of power start to change, you're not going to have fly ash as readily available. And so there could be other things that may be coming out on the market. There are fly ashes that have been put into landfills that could be remediated and used in concrete. We may be looking more at natural blends as sources. And so just as the market dynamics change, we may be looking at different sorts of supplementary cementitious materials in the future. And then something that I think is interesting is that I see a lot in terms of 3D printing technology, kind of still at the university and research level, but that type of technology, if that starts to get utilized, could actually make different blends more viable, or different blends are going to be better applicable for that sort of placement application. Then, as we've mentioned, aggregate selection for optimizing the member size and lowering the cement content is another lever that a mix designer can utilize. As we mentioned, Orca, I can just speak to this from my own experience, has properties that result in concrete with low deflection, high modulus of elasticity, high strength, low shrinkage. And then also has the benefit, because of those, that you can get better material efficiency out of your cementitious materials, which results in being able to design a mix with less cementitious material. And so then on the design side, if there are applications or projects where having a high modulus of elasticity or low deflection is important, and this was something that Don mentioned in his presentation, then that could be something that would be specified when it's going to make a design difference that allows you to make smaller member sizes, or just kind of optimize your design in that case. And so with this, having a performance specification and specifying those material properties are actionable items. Then with admixtures, there's a variety of options here and admixtures that we work with as ready mix producers. One thing to consider is that with synthetic and steel fibers, you can replace certain levels of reinforcement. And so this is something to consider for a project in order to reduce the amount of rebar. There are fibers that can be put into concrete that allow that to be done. Then there's also newer admixtures available now for doing higher concrete flow with less cementitious powder, new admixtures for doing higher strength with less cementitious powders. So these are all things that are available and that I'm playing around with, my team is playing around with in the lab as well, to look at where different potentials that we can be using these things, again, to further reduce the embodied carbon. And then all of the admixtures that we've had for years also help provide flexibility as material supplies change and we're looking to develop new formulas. And so again, performance specification is going to support being able to have flexibility to do this. Also consulting with a concrete supplier or an admixture supplier for alternative slab designs where you can eliminate either eliminate reinforcement or replace some of the reinforcement with fibers. And then sequestered CO2, this is kind of some of the newest topic out in terms of concrete sustainability. Carbon Cure has a technology for injecting recycled CO2 into ready mix concrete. Everyone that's working with CO2, kind of the idea behind it is that with concrete, you have the elements in place to be able to turn the CO2 into calcium carbonate, which is limestone. And so with this, a performance specification encourages the use of this. And future technologies that I've seen presented on that I am aware are being worked on by others out in the industry are looking at doing higher quantities of sequestered CO2 by developing coatings that go around aggregates. Again, this goes back to with aggregates being a significant amount of volume, that's a great opportunity to look at in trying to do more sequestered carbon and ultimately lowering that embodied carbon of concrete mixes. Treatment of recycled water from concrete production is another piece in research. And then also ultimately looking at just doing higher quantities of injected CO2 just in concrete could be something that comes on in the future as we get more comfortable with working with this type of technology. And then lastly, looking at the use of waste products and recycling. Recycled concrete aggregates is something that I see as a big topic, just in the American Concrete Institute committees, also in research with universities. Some municipalities actually require or allow it for use in minor concrete or street base. And so actionable considerations here are to understand the local recycled concrete aggregate sources and the concrete suppliers QC program, because that can help you gauge then what type of applications you want to be able to use it in. Allowing the use of recycled concrete aggregate in non-structural concrete applications is something that's a pretty easy thing to implement. Something I will say is that I am familiar with there being challenges in freeze-thaw environments with durability. And so it's not that it can't be done there, but that's something to be aware of and talk to your ready mix producer about. And then with this, I think there's also university research opportunities. Kind of future considerations, I'm aware of efforts where different committees are developing guidelines for quality and also publishing data regarding recycled concrete aggregate. So as an industry as a whole, we have a better understanding and have enough data that will make engineers comfortable with using this product. Also, I've seen a company that is working on producing plastic aggregate, and that still has some more work to do in terms of utilizing it in concrete and what's the best application for that. But that's something that's been proposed. And then lastly, I just wanted to touch on the use of technology. This is another way that concrete ready mix producers can be moving forward, and something I think we'll see more in the future. There are tracking systems on trucks that allow the measurement and management of slump, temperature, and additional water in transit, or even admixture in transit can be done automatically. And so this allows a lot more transparency now and a lot more data. And as more of this data gets collected, then we can be using this more to do things more efficiently. Maturity testing is also a great solution for doing in-place constructability strength, and particularly when you're doing high cement replacements, this can be helpful in those applications. And then we also have programs to calculate things like the anticipated service life against chloride corrosion, and that allows us to refine mix designs. And then looking towards the future, things that are being worked on right now on the research side is artificial intelligence. There's several projects and groups that are working on trying to develop algorithms that will utilize all this data that's being collected. So now we're at a point where there's a lot of data out there in terms of mix design strength and talking about the tracking systems on the trucks, and now trying to take that all together and use it to either do mix optimization prior to a submittal, or potentially rethinking the way in the future that performance is accepted or verified, or even allowed to adjust mix designs to do in-place conditions on the day of. So these are all things that we can be thinking about for the future, and ultimately to implement those will require cooperation between both the design community and material suppliers and contractors as well. And then also, I think we're also going to continue to improve just the embodied carbon measurement and being able to compare materials as well. And the EC3 tool is a great way that we're continuing to move that forward. And there are a lot of groups working on what are our methods of measuring and how do we do this. So with that, I just want to say thank you for the opportunity for putting this together.
Thank you so much, Alana. Yeah, that was great.
We're just hitting up on 6:30, which was the scheduled end time for our event. So I'm going to keep the Q&A pretty quick. We did get several great questions from the audience in the chat. So I'm going to start with one that was directed at Dirk during his presentation, but I think in a more general sense could be answered by anybody. The question was from Simon Reese, and it was, Dirk, was there a significant cost premium for reducing the cement content by using the aggregate from British Columbia rather than local aggregate? So I guess Dirk can answer for the specific project, and if anyone has some more general thoughts on cost, that would be great to hear too. Oh, Dirk, you're muted.
Thank you, Laura. So no for that project. I don't know the specific numbers, but there, in general, we were working under constraints to keep everything cost neutral or very close to that. I think National can probably speak better to the trade-offs that occur. Being largely that there's less of that it enables less cement, though the aggregate piece has the transit cost.
This is Don. I'll agree with Dirk. I'll defer to John on the real numbers. On our project for Brookfield, the switch was made as a no-cost add to the project, so we got it at no charge. It was actually part of the negotiation of when they were being selected for the project. What does that mean as a true cost to them, though? I think John is the one that probably knows the real number.
I think John might be muted.
Okay.
John, are you still on? I think you need to unmute from your phone number and not from your name on the Zoom chat. Luke, are you able to unmute John? I'm trying to unmute him and it's not working. Oh, there we go.
Sorry about that. I was getting another call. I don't have the exact details about the costs, price differences in the examples that were mentioned, but generally, switching over to the import material reduces the cement content. So cement being one of the higher costs materials involved there. And whatever pricing of the materials are, it could be neutral, as those the gentlemen were indicating. So probably net zero cost, because there's a higher cost for a premium aggregate, but you're losing some of the cement. I hope that answers the question.
That's great. I think that's exactly what we all want to hear, is that we can really reduce carbon without adding a lot of cost.
Correct.
One of the other questions we got was, at what phase, I think this was to the designers, what phase do you look to engage suppliers? And I guess suppliers can answer this too. What phase do you want to be engaged at?
Well, I'll take my turn on that. This is John again. As soon as possible, really. It's really interesting. I think Don was talking about thermal control, and in the traditional method of the phases of the project, as a ready-mix supplier, your contracting estimators, they don't even know what's required on thermal control, right? And then at the 11th hour, it's this aha moment. We need to come up with some thermal control plan, and it's like, I don't know. It says foundations. You didn't even give us volumes. We don't even have an indication of whatever. So I think as early as possible would be my, and I don't know really on the engineering side what their thoughts are, but as soon as possible, in my opinion.
I might give just a quick example of a project. This is what we did on the Microsoft project in Seattle, but we wanted to push the industry on low carbon concrete. We want to push the industry on these EPDs. And one of the things we did was probably when we were still in, maybe I'll call it the into schematic design, where we had ideas how much concrete was going to go in the project, but before we had actually designed anything, we held a workshop where we got most of the main suppliers together, and it was honestly 6 to 8 months before the actual bid was going to come out. And we had what we called the low to no carbon workshop. And we talked about what are all the variables that are out there? What is it we could do to make your life more, allow you more flexibility to be more aggressive? And we created a table that was going to be the performance-based mix table of what we needed for criteria for our mix designs. And then I put it on the table and just said, okay, guys, you're going to see this as a bid. This is what's coming to you in 6 months. You have 6 months to act on it. And the key with that was telegraphing, if it's a big enough project, telegraph your intentions early to let the suppliers see what's coming and give them time to react. So kind of like what John was just saying, they're not just seeing it at the 11th hour where they got to take whatever's on the shelf and that's what you got. Give them time to actually do something. And if it's a big enough project or they're seeing enough of the same consistent ask coming to them, which is a big key, they have time to do something. And then that's one of the ways that you can really start to drive some of those innovations. So earlier is better for sure.
Okay, I'm going to do one last question and then we'll wrap up since we're running a little bit over. What was the driver on, I guess to both Dirk and Don, what was the driver for lowering the carbon of the concrete on the projects you worked on? Did it come from the owner? I guess, did it come from the design team? Like where did that come from, and where do you think that will be driven by in the future? Or who do we need to talk to kind of really put the pressure on to get people to reduce the carbon of concrete?
Dirk, I'll let you go.
So our project was a combination of the owner's goals, although I think every owner doesn't necessarily, owners are just learning about embodied carbon and the embodied carbon of concrete. So I hope we have some owners on the call today who are listening as well. But that goes through the architect, the prime design consultant, and then the engineer. So we had goals from the owner that were broadly in terms of sustainability, in terms of carbon. They were using LEED as a tool. The fact that the LCA was in LEED and it helped with their score was an important point. The details of the LCA to the level we did it, had it not been part of LEED, might not have happened. The strategies of reducing embodied carbon, many of them I think would have happened, although it might not have been put together so nicely in numbers and reductions, because we try to take what we learn on job A and apply it as options at minimum for the next one and kind of build upon that. So I think that it will come when the owner really lays it out. That's great, but we as designers have to educate, and we have to bring it up, and that's very, very important. Don, I'll let you build on that.
I'd iterate a lot of the same. It is without question our owners set the table of what we choose to prioritize and act on, and frankly also set the bounds of how far they could go. I'll say on our project, the owner had high sustainability goals. They had aspirations. They really didn't know where it was going to go, but there was a tension inside the ownership side also. Hey, we want to do this, but it can't cost it. We don't have an unlimited budget, and we really need to know where we're going before we go there. And honestly, being able to show win-win scenarios where they could reduce carbon and at least be carbon cost neutral at the same time, that's really, they said, you can do that. That kind of a message is what then gave us the latitude to push some things forward and get them to kind of back up what we were going to do and let us be creative on what we're going to do. So you have to make the business case to them. But without question, I think the owners set the table that what we do. What we are seeing right now, though, is especially in the tech sector, the tech clients are getting pretty sophisticated on this topic pretty fast, and they are starting to drive. They're asking hard questions that they're looking for us all to respond to. And so it kind of behooves us actually to be on top of this and help them push some boundaries and frankly partner with them. That's actually how EC3 got created to begin with.
Alana, since you're on the cutting edge of the future here, do you see a lot of opportunities for these win-win scenarios where we're reducing carbon and maybe we're keeping cost neutral or reducing costs?
Yeah, I think there's definitely a lot of ways to do that. I think something that is a challenge with that a lot of times can be schedule. The rapid schedule can sometimes make that really a challenge to achieve. But yeah, there are definitely a lot of opportunities to do that cost neutral.
Awesome. Thanks, everybody. Luke, I think we need to wrap it up.
Yeah,
so we don't
I
keep
think
everybody too
right.
late.
I want to be really respectful of everyone's time. Thank you so much to our panelists for taking the time. I mean, I love what you all are doing, and thank you for sharing that knowledge with this group. Yeah, so a silent Zoom applause, which is never very as
we can
satisfying as we
unmute
like,
everybody and let them all applaud. Let's do it. Everybody applaud.
Sounds dangerous, but there we go. We'll so we'll try to follow up with any unanswered questions, but again, just a big thank you. I think this is a really important thing to understand. You know, concrete's in all of our projects, so it's great, great presentations.
Posting this on YouTube, right?
Yeah, we'll follow up with all the links, everything you need. It's been great, and we'll continue this discussion in a different form, you know, next month. So please. Yes. Sign up for email updates if you have not already. And
I apologize that we couldn't get to everyone's questions, but I think everybody is on LinkedIn or in the Carbon Leadership Forum online community. So let's keep the conversation going there.
Too much great information. All right, with that, I think we call it a night. Thank you, everyone.
Thank you.
Thank you.
Thank you. Good night.